The second speaker in this session will be Professor Abdelkader Outzourhit.
Yeah, go ahead.
Okay. So, from the physics department of the University of Qadi Ayad in Marrakesh, with the title Perovskite Solar Cell, Recent Advances and Next Generation Applications. So, Professor Outzourhit is eminent scientist in this area, and he also is a very good friend of mine. And let's say he's the responsible that I am here, because 17 years ago, we made our first bilateral project in collaboration between Portugal and Morocco, let's say many years ago. And after that, in this period, I came a lot of times in Morocco. I meet a lot of people. We made a nice network. We receive a lot of Moroccan students in our lab. So thank you.
Thank you. Thank you for this nice presentation. I'm really glad to work with you, and we look forward to developing more collaborative work, especially with the network is growing. With the InSAM’ conference, we're really able to grow the network. So, my presentation here will talk about perovskite solar cells, and I'll be more interested in the next generation applications, and also on the recent development. But I'm sorry, in order to understand what's going on in this field, we have first of all to go through the basics. Okay, so I have to show you the structure of a solar cell, and then see what are the different materials and layers that are in the solar cell, so that we can understand the problems, and then what are people doing to solve, to overcome those problems, especially to enhance the efficiency, the stability, and all what has been said in the last conference. In the last conference, you have seen the silicon technology, but in order to understand those improvements in efficiency, we really have to understand what are the problems, first of all. In order to understand the problems, we have to go to the basics. What is a solar cell? I'm just going to spend a few minutes just showing you the structure of a solar cell, basic structure, that will help you understand what are the problems in these devices. Okay, so in fact, this it's a part of a tutorial that I usually give to students, about solar cells and PV. So I start with this basic structure of a solar cell, which is very simple. It is made of what we call an absorber. That's the material that absorbs the light and converts it into free electrons and holes. But the absorbers alone won't work, because you need to separate those charges you create and collect them. So in order to do that, you have to sandwich the absorber between two functional layers, the blue one and the red one. Here, the blue one, I just said it's the layer that will allow us to extract the electrons, and the red one is the one that allows us to extract the holes. That way, we extract and we collect and we separate the carriers. Okay, the carriers are created by light, by photons, and the photon energy needs to be higher than the binding energy of those carriers within the semiconductor, because usually these carriers, for example, in the case of silicon, they are a part of covalent bonds. So in order to get them out, you have to excite them. You have to give them enough energy to escape from that covalent bonding. Once you create the electrons, it leaves behind a hole, which is a positive charge, and this electron here is free to wander around. Okay, unless it comes back to the, and also the hole here is also free to ride along in the semiconductor. But the problem is, you have a lot of space there. They have to travel a long distance in order to arrive to the interfaces there, so that they can be separated, okay, and collected. And then you have, in the cell, you also have some contacts. Those that emit the The gray contacts here, those are metallic contacts that allow us to collect our cell to an external circuit, load here. Okay. The front contact is where the light comes from, so it should be transparent somehow. It should leave, otherwise, no light will get into the absorber. And the back contact, it can be either transparent. In this case, we talk about what we call bifacial solar cells. That's what we heard, in the last presentation. In bifacial solar cells or bifacial modules, the cell can be, eliminated from both sides. So this contact is also transparent. It's like fingers, so that light can get into the onto the absorber. Okay. So here I just put P-type and N-type semiconductors. But this is the basic structure. I'll explain why do we have to have P-type and N plus and P plus. Those are just some notations for the doping level. So from the energetic point of view, this structure, the energy levels, are designed so that electrons they can go down the steps like this. If you create an electron, they can because electrons they like to lower their energy, so they can come this way along these steps, and the holes they can go up the stairs like that. That's how they lower also their energy. Okay, so from the energy point of view, the solar cell is also designed this way so that you can facilitate the separation of the electrons and holes. Okay, and then you collect them, and then once the electron comes here, you have a potential difference that will drive a current in the external circuit. So basically, this is the solar cell. So we have what we call the active layer. So this is the absorber, where the photons give rise to free electrons and holes. Not only free, we'll see. And then you have what we call the functional layers here, that allows us to kind of selectively separate the carriers. There is one which is called HTL, whole transport layer, and one which allows only electrons to go through. It's called electron transport layer. These layers, as you see, they are very thin. It can be around 50 nanometers because their only function is to allow this separation. Okay. If we shouldn't, the light shouldn't be absorbed here. Okay, since this is what we call parasitic absorption, it won't lead to the creation of electron hole pairs that you can collect. We'll see why. We'll talk about this later on. And another thing here, if you want this separation to happen, you should have somehow an electric field here that allows only electrons to go through. So the electric field should be directed this way. So the electrons, can be attracted to the inside. And at this interface, there should be also another electric field that goes this way, so that only the holes can go through. The electrons are repelled back. Okay. If you don't do this separation, you won't have a potential difference. If you mix electrons and holes, you don't. But if you arrive to separate electrons in one side and holes in one side, you'll have a potential difference at the open circuit, and then if you put a load, you can drive current. Okay? So this is the basic structure of the solar cell. Okay? So the heart of this cell is the absorber, which is usually a semiconductor. The semiconductor, as you know, you can liberate electron and holes in the semiconductor with energies that are in the solar spectrum. In the, let's say, in 1 to, let's say, 3 electron volts. If you cannot use insulators, because insulators, they need higher energies to liberate the pairs, and they are poor conductors. Okay. Metals, everything is already free, so you can't do it. So the only choice is semiconductor, because you can liberate electrons with energies that are in the solar spectrum. Okay, the photons that are in the solar spectrum. That's why I use semiconductors, mainly silicon, as we'll see. Okay, so this is the basic structure, and what are the main steps that are involved in the solar cell? So there are basic steps. So first of all, there is the absorption of a photon, and the photon has to have an energy that is greater than the binding energy of that electron in the covalent bond. That binding energy we call band gap energy somehow. So there are two ways you can. Once they are liberated, the electron and holes are liberated, they have to travel somehow to arrive to the selective contacts. How can they travel? They can travel either by diffusion, because you create an excess there, so you have an excess of electrons and holes where the photons are absorbed, so you have an excess, you have one driving force is diffusion, and the other one, if there is an electric field, they can also help in transporting the electrons to the interface. So this is called, one is called diffusion limited, if only diffusion is the dominant process, and the other one is drift limited if there is an electric field here, which helps those electrons to move. Okay, but once an electron arrives here, it can go because the energetics are favorable for it to go, but the whole won't go here. Okay. Okay. The same thing here. If an electron arrives here, it will be repelled back because there is an electric field, what we call the back surface field. Yeah. BSF. I just put it in that direction. And also the energetics. If you look at it from the energetics point of view, an electron has to jump this barrier to go here. Okay. Okay. But the whole, it goes easily. So this way you can separate the two, the pair that you create, and you create a potential difference in different current and so on. So, but the only problem is when you excite the electrons, you don't create immediately free carriers. We create what we call an exciton because the electron and the holes are tied by an electrostatic force because it's positive charge and a negative charge. So, but luckily in semiconductors like silicon, that binding energy is very low. It's on the order of, let's say, 10 milli-electron volts. So, they are dissociated at room temperature because room temperature energy, thermal energy is about 25, so it's higher than the binding energy. The problem arises in organic materials where the electric constant is very small and the binding energy is very high. So there you need other mechanisms to be able to separate or to dissociate the excitons that you create. Because what you create in the beginning is an exciton. It's a bound electron hole pair. And then the exciton dissociates either because of the thermal energy or if there is a donor or acceptor, you can dissociate it. I'm not going to go into these details. And then the third step is the diffusion or drift, as I said. The diffusion, why diffusion? Because you create an excess, large concentration of electrons there and holes, they diffuse. But they diffuse in either direction. But I told you that if electron goes this way, it will be repelled back. If it survives, it can arrive to the we'll see there is also survival time of electrons and holes because there is the reverse process, which is the recombination. Yeah. So we'll see also, and then the separation at the interfaces and the connection. Okay. If you are at open circuits, that means this is open circuit. You will have accumulation of holes here and electrons here, so you have what we call the open circuit voltage. It's like a small photo. On appelle en français photopile, a battery that is pumped by photons. Okay. Okay. It's not like a. All right. Okay. These are the basic steps that are involved in the source. But the problem is, what is the origin of this field here, the front surface field or the back surface field? Because this is only the band diagram, what we call it's a flat band potential diagram. It's when the bands are flat, but we have, the bands are not flat like this. This is just a way to represent the energetics of the system. What happens when you put in contact a P-type and an N-type semiconductor? So you all know from your classes of some semiconductors that you'll generate what we call a built-in voltage or an internal electric field. Okay. So let me see it. I'm just going to jump this. So this is, for example, a P-type silicon. It is doped with boron, which has 3 valence electrons. Okay, and each boron atom that you introduce, it introduces a hole. This is an N-type silicon, which is doped with phosphorus. Each phosphorus atom, introduces 1 electron. So it's an N-type doping. So what happens when I put together an N-type and a P-type semiconductor, this is it is not an equilibrium because you have an excess concentration of electron on one side and an excess of holes in another side, so they will tend to diffuse. Okay, but if an electron moves from the N side to the P side, it will leave behind here a positive and uncompensated phosphorus ion. Okay, because the electron belongs to the phosphorus in the beginning. So, and if a hole, diffuses from the P-type to the N-type, it will leave behind a negative boron ion. Okay, because that hole used to belong to the boron atom, which is neutral. But if the hole leaves there, that means that that hole is occupied by an electron, and the boron becomes effectively negative. So, as you have this movement, fixed charges start appearing at the interface between the two. Positive in one side, in the inside, and negative in the this side. And there is an electric field, a built-in electric field that appears. At the equilibrium, we have what we call the diffusion current of majority carrier from the inside to the P side, and there is also a minority carrier current, which is a drift current in this case, because if you have an electron here, it can cross this junction easily. So it will be proposed by the electric field. So at the equilibrium, the two currents are identical. So we reach a situation where there is an equilibrium electric field, which is called the internal electric field. Or you can also think about it as a potential, a built-in potential, or you can think of it as a barrier, potential barrier. Right? So there are lots of ways you can imagine what's happening here. So you can see that this electric field opposes the injection of electrons from the N side to the P side. Because the electric force in this side. And it opposes the injection of holes from the P side to the N side, but it doesn't oppose the passage of minority carriers, what we call the minority carriers. Okay. So this is very basic in order to understand now the origin of this field here, okay, the front surface field. So this is basically an N-type and a P-type, but in plus meaning just it is the doping density is higher here than in here. So for example, if this is 10 to the 16th, this should be 10 to the 17th or 18th, okay, per square centimeter, cubic centimeter. The same thing, the P plus here means that just this is much doped than we have more, for example, boron atoms here than in here. Okay. So anyway, even at this junction here, you also have an electric field. You can easily show that you have also what we call the back surface field that is pointing in that direction. And that back surface field, you see that it blocks electrons, but it favors the passage of holes. The front surface field, it blocks the holes and it favors it lets the electrons go into the N plus side. Okay. Okay. So this is basic operation principle of a solar cell. And now we'll see what type of material we use here and what are the type of materials that we use here and so on. Okay. For a p-n junction, one last thing. I think you did this p-n junction. You can bias it. You can either bias it by reinforcing this internal field. If you want to reinforce it, you have to reverse bias. That means you put a negative terminal here on the P side and the positive terminal on the inside. If you forward bias it, you reduce the effect of the internal field. You just have to put the positive terminal on the P and the negative terminal on the N. So that way you create you lower the barriers and you allow the injection of electron. So with the reverse bias, the current is very small, okay, because you only have what? Minority carriers current, because of that. The field blocks, the majority carriers. But in the forward bias, once you pass the given threshold, you have an exponential rise in the current. Okay, so that's the positive bias, and you have really the diode equation here. Okay, and the current is usually increases exponentially with the voltage. That's the ideal diode equation and so on. So we'll come back to this. For the semiconductors, you know, the common semiconductors that are used in PV or, you know, silicon, it's a group 4, germanium, and then you can have binaries like gallium arsenide, aluminum phosphide, and so on. So these are called the 3-5s. So we have the group 4, the 2-6, one element from column 2 and one from column 6, and also the 3-5s, 1, 3, 5, 6, 2, and so on. The nice thing about these, they all have an average valence of 4. Right? If you do the count, you have 4 electrons, valence electrons on the average. You have 2, 6, 2 plus 4, so 6, that's 8, divided by 8, that's 4. 3, the same thing. 1, 3, 6, 2, that's 16, divided by 4, that's give you in the average 4 valence. Everything revolves around silicon, the group 4, you know. And each semiconductor has its own banding gap energy that is needed to excite that electron. And the nice thing is that, you know, the efficiency, the theoretical efficiency of solar cells varies with the banding gap, and it has a maximum around 1.4. Okay, that's what we call the Shockley-Kaiser limit, which is the thermodynamic limit. So the maximum is around 1.4. That's why people are very focused on studying the semiconductors that have banding gaps in that range, 1.4, 1.5, because the maximum Shockley-Kaiser limit, as you can see here, this is the maximum theoretical thermodynamic limit. The maximum is around 1.4 here, and these are just the experimental values for different semiconductors. Okay, so now, in order, again, to understand the processes that happen on the solar cell, we have to see what happens when you shine light on a semiconductor now. When you shine light on the semiconductor, evidently, if the energy is higher than the band gap energy, the photons will be absorbed, okay? So if the photon will be absorbed, that means that the intensity or the photon flux will decrease with the depth. Yeah. It decreases exponentially following the Beer-Lambert law. Okay, alpha here is the what we call the absorption coefficient, and x is the depth in the semiconductor. So I'm shining light in the semiconductor. I'm just shining. I'm irradiating the semiconductor with the power density Gi, which is in watt per square meter. So that's just the power per unit area. Gi is called the incident irradiance. Yeah, and you know the nice thing is here is this absorption coefficient here, alpha. It depends on the type of semiconductor you have, and for each, this graph here shows you the absorption coefficient of common semiconductors that are used in solar cell. The red one here is the famous one for silicon. Okay, the blue here is gallium arsenide, and for cadmium telluride is this 31. Let's first of all just understand what this law means. Tells you that the photon flux decreases exponentially because of the absorption. Yeah, but it has another meaning. It just tells you that if you just do some differentiation of the equation, you'll see that the alpha has a meaning of a probability density per unit length that the photon is absorbed. Alpha, it just tells you that it's the probability per unit length that the photon is absorbed. Okay. So it's a probability, in fact, density. Okay. So it's called the absorption coefficient, but it has another meaning, which is the probability that the photon is absorbed within a per unit length. Okay. And okay. So that's the physical meaning of alpha, and also the physical meaning of the Beer-Lambert law. It just tells you that it gives you the probability that the photon is absorbed in this gx, in this small trench gx, and it's proportional to gx. Just see that this probability is proportional to gx. And the probability constant, the constant is just alpha a. Okay. And another meaning of alpha, 1 over alpha, it just gives you what we call the absorption depth. The absorption depth. It just gives you the depth over which the photon flux will decrease by a factor of E. E is 2.7. It's going to be divided by 3. So this gives you a characteristic, let's say, thickness that your semiconductor should have in a solar cell. Because the thickness of the semiconductor should be at least greater than the absorption depth. Otherwise, the photons will not be absorbed effectively. There will be some photons that will escape from the semiconductor. Because at the absorption depth, you have 36% of the photon flux will be absorbed, and the rest will go through the semiconductor without absorption. So, and we'll see that value is very interesting. Okay, and alpha, the absorption coefficient is usually measured from the transmission reflection measurements, as you know. But let's just find some orders of magnitudes of alpha, and you have to believe me that the photons that are really effective in solar cells are those that are close to the band gap, to the threshold, because this is the threshold wavelength, but you can also think about it as threshold energy, because this is the wavelength. So the photons that are in this region are most effective in the case of silicon. The photons that are in this region here are more effective for the other semiconductors. We'll see why, because if a photon has a large energy, that means you will you will be left with an electron which is highly energetic, because the energy that you need is only the band gap. The excess energy will just be lost to the lattice, and we just heat up the cell. And when you heat the cell, you're losing in efficiency. Okay, so as you can see here for silicon, the absorption coefficient around the band gap is about 10 to the power of 2. Okay, centimeter minus 1. So the inverse is just 10 to the minus 2 centimeters. That means what, 100 micron. So the thickness in this case for silicon solar cell should be greater than 100 micron. Okay, but for cadmium telluride, for example, you see that the absorption coefficient is around 10 to the power of 4. That means what? It means that the thickness in this case should be on the order of what? 1 micron, because 1 over 1 to the 1 over 10 to the minus 4 centimeter is just 1 micron. Huh? So, meaning that these semiconductors are ideal for what? For thin film solar cells, but silicon here, crystalline silicon, you only have to make a very thick solar cells out of it. Huh? Otherwise, you lose a lot of photons. So that's basically there. Another thing that you should notice is highly energetic photons. They have absorption depths that are very small. For example, this photon here, in the case of silicon, will be absorbed at around 1 micron from the surface. So each photon here in the semiconductor, when you irradiate your solar cell by light, each photon has the chance to be absorbed in a given depth. And this is very interesting for us for the characterization of solar cell, because you can see, it can give us an idea what's happening at different parts of the cell, either at the front surface, the door, or the back surface, etc. Just by looking at the efficiency, okay, of the cell for a given photons, as a function of photon energy, or as a function of what wavelength, okay? And that's called what, the external quantum efficiency. I'm going to talk about it later on. Okay, so I didn't talk about the difference. Why is this way and why is this way? Because this is an indirect band gap, and this is a direct band gap semiconductors. Usually direct band gap semiconductors, they have high absorption coefficients because there is only one process that is involved in the absorption. But in indirect band gap, you have at least 2 processes, so the probability, you remember alpha has a probability, it's like the probability of a photon being absorbed, it's going to be lower, okay? So that's why those are I have some questions here for students, but they can look at them and try to answer. So what is the minimum thickness now of your absorber? The minimum thickness should be at least equal to the absorption depth, okay? Minimum. Okay. But there are other processes that are going on in the solar cell. The other one is the inverse there is a photogeneration, because once the photon is absorbed, it gives rise to a pair of electron hole, and we can suppose that the quantum efficiency in this case is 1. That means each photon that is absorbed gives you a pair, but which is not the case, in fact, because as we'll see in the measurements, the quantum efficiency is less than 100%. So it gives you the photocurrent. If you suppose that we collect all those electrons, the photocurrent is proportional to the irradiance, and so on. Okay, and the other process that is going on is the recombination, and the recombination is the annihilation of a pair. That electron going back to the holes or vice versa. Okay, but in that process, there is some energy that will be released. Okay, so this energy can be either a photon. We talk about, in this case, a radiative recombination, or it can serve to excite another electron. This is what we call recombination by Auger process, or it can be even mediated by a trap within the band gap, and this is called Shockley Hall recombination. So there are several pathways for the recombination, and for us in solar cells, the recombination is a loss. We should minimize recombination, because we generate them. In fact, we need to collect them instead of losing them, because if they recombine, it's a loss for us. So this is one of the main losses in solar cells, is the recombination. Okay? The recombination of electron hole pair. Okay. What else? Okay. There is another. Since there is a recombination, okay, so automatically, that doesn't happen instantaneously. Once you create a carrier, either a hole or an electron, it has it can survive for a certain time, and this survival time is called the lifetime, or the minority carrier lifetime. Why minority? Because the minorities are more sensitive to recombination than the majority. Because the majority, there are a lot of them, so they're not very sensitive to the recombination. But the problem is with the minority carriers, they're very sensitive. So that's why in solar cells we pay attention to minority carriers, because they're very sensitive. Their concentration is very sensitive to the recombination process. Okay. Okay. Again, the survival time, what's it called, the minority carrier lifetime. 1 over that is just the probability period time of recombination. Okay. It's just the probability period time for recombination, and we can even determine what is the recombination rate, how many carriers recombine per unit time, per unit volume. That's called the recombination rate, and the recombination rate is just proportional to the excess of carriers that you create by light or by whatever, or by temperature, and the recombination, the carrier, minority carrier lifetime. And then if you do this will give you an exponential decay of the carrier concentration. Once you just imagine, you just shoot a photon pulse on the semiconductor and you stop it, you create an excess and you let it decay. It decays. Why? Because of the recombination. Because the carriers, they decay. So we get a decay, and from that decay we can get the carrier lifetime. And this is the photoluminescence decay. The photoluminescence, because you have luminescence, meaning that you have a radiative recombination, and if you have radiative recombination, the intensity is proportional to the minority carriers that you have. So the intensity is proportional to the minority carrier concentration, and this carrier concentration decreases exponentially, and from that decrease you can get the carrier lifetime. Okay. This is how we measure the carrier lifetime in semiconductors. It's very easy with the photoluminescence decay. And from the photoluminescence decay, from the carrier, minority carrier lifetime, you can also get what we call the diffusion length. And this is a very important parameter in solar cell, because the diffusion length just gives you distance. Imagine that you travel blindly like this. That gives you the average distance that you can travel before you it fell in a hole or something. That means that it gives the distance that a carrier can travel before it recombines. Okay? That's the definition of the minority carrier diffusion rate, or it's the mean travel distance. Again, your absorber, the active layer, the thickness should be less than this parameter. That way, you reduce the recombination. Okay? So now we have two parameters. One is the absorption depth, and the other one is the minority carrier diffusion rate, which govern the thickness of your absorber. Okay. So as I said, the recombination is a loss, so we need to reduce it. How? Well, you have to understand the nature of the recombination centers, what you call the recombination centers, where the recombination happens, and also try to eliminate and passivate those recombination centers. Okay. One problem is the surface of semiconductor. That's where a lot of recombination centers are. The surface, as you see, is the discontinuity. Let's say, for example, the surface of silicon, instead of having 4 neighbors, the atoms on the surface, they only have 3. So, since silicon has to have 8 electrons, okay, there is one, what we call a dangling bond. Okay, the dangling bond, in the language of chemists, is just a radical, but it is immobilized. It's not free. Okay, it's like a radical because this silicon here has an electron that is not paired with anything, and we call it a dangling bond. Okay, and those are really, they can trap electrons, and they can also trap. That means they immobilize the electrons, or they can also just recombine. Recombine them. Because trap meaning if you trap, you can release. There is a probability that the electron will be emitted later on. Okay, so those are main source of recombination in materials. The dangling bonds, you can find them where? On surfaces or the grain boundaries. Because at the grain boundaries sometimes, or if you have cracks or whatever, grain boundaries, you have discontinuities, you can have some dangling bonds there. And those are killers for efficiency in solar cells, the dangling bonds, because they can recombine, they can be centers of recombinations. Okay? And the dangling bonds are also very reactive. The chemists, they know that the radicals are very, they react directly to anything. So you can also participate in. So you see all the work that is going on in solar cells. Even in silicon, they're trying to passivate or to render these recombination centers inactive. So they don't trap electron. Because the purity of silicon now in the bulk is so high that the bulk is not a problem anymore. It's not the bulk of the semiconductor which is a problem. It's its surface. Okay? You have to eliminate because surface is discontinued. You have a lot of. I'm talking about silicon. In other materials, we also still have problems with the bulk defects and things like that. Okay, so now let's see what are the most common recombination centers, and then so we can have what we call point defects. You know, point defects, vacancies, and interstitials or anti-sites. I hope you know anti-sites. I mean, those are either missing atoms if you have vacancy, or atoms in wrong positions. For example, you have an interstitial, an atom that should be in a lattice point is inside an interstitial side, or an anti-site. That means atom switching side, side. Okay, those are all centers of recombination. Dislocations, those are just line defects and things like that. The grain boundaries, because grain boundaries, you know, there are some misalignments between the grains and things. You have a lot of defects and impurity and defects, and also dangling bonds. You can have impurities if your semiconductor is not very pure. There are also recombination centers. And as I said here, surfaces are really a big problem. Okay. I'm still talking in general, okay? Yeah, you have to stop me if give me.
So we're 15.
Huh? 15? Only 15? Oh, okay. Then it goes fast. Okay.
20, let's say.
20. Okay. Well, no, I finished. So, the objective here is to passivate those defects, is to eliminate them somehow. Okay. And you'll see the technology that you saw in the last conference, either the PERC, the TopCon, or the Pearl technologies in silicon. That's what they're doing. They're trying to passivate the surfaces, because that's where the problem is of silicon. So you have what we call chemical passivation. You just react the surface, for example, with hydrogen. For example, in the case of silicon, hydrogen will be linked to the silicon dangling bonds, and okay, you can treat with other chemicals. You can deposit a thin film, what you call physical passivation. Just put a thin layer of some material, an oxide or nitride, or you'll see in silicon, that's what is used a lot to passivate the surface of silicon. You use amorphous silicon or silicon nitride or aluminum oxide or silicon dioxide. Okay, you can, for example, try to anneal your semiconductor just to do dangling bonds, because you can create what we call reconstruction of the surface. Those dangling bonds, they can be tied by. Or you can do a plasma treatment also, because if you treat the surface with the plasmas, are very reactive also. So you can introduce reactive species that will bond with those dangling bonds, okay? And that way you can passivate sorry. You can also coat with organic molecules. You can adobe. That's called adding certain bonds, or surface reconstruction, that you have to heat up the semiconductor, and then the bonds at the surface will rearrange, so that you eliminate those dangling bonds. Okay? That's what we call a surface reconstruction. And for example, probably Professor Hamid in his presentation on surface techniques, maybe he will talk about this surface reconstruction. Okay, now, suppose that we eliminate all these effects. Now we shine. This is the IV characteristic of your PN junction. Now, what happens when you shine light on it? Well, so you just add a photocurrent to this, because you create photo-generated carriers, and you create a photocurrent. So this curve here will just slide this. Oops. Sorry. I'm gonna move a little bit, because so this is it. So it just shifts down. There's a little bit of animation like this, here is the dark, I shine light, so this will go down, because you adapt a photocurrent, here that will adapt to this. And it depends on what is the convention you use. You use either the generator or the receptor convention, so you can multiply this by minus one and just shift the curve upward. So this is basically the response of a solar cell when you shine light on it, and you have some what we call characteristic parameters of the solar cell, the current, the short circuit current, the voltage at open circuit voltage, and the voltage at the maximum power points, and you get a lot of information from the characteristic. So this is I just inverted this characteristic, and from there you can get also the efficiency, which is the output power divided by the input power. The output power, we have to determine the maximum power that we can extract from the cell, because it doesn't make any sense. You have to extract the maximum power from the cell. So use it at the maximum power point, divided by the input power. It's just the surface of the cell times the incident irradiance. Okay, and you can also express that in terms of field factor. The field factor is just the ratio of the area of this rectangle, EM times VM, divided by the area of this bigger triangle, which is the maximum power that you can extract from the cell. The maximum is just the OC times the short circuit current. And you can also, therefore, you can put this to what we call the power conversion efficiency, some electrical parameters, and also we can get the one parameter is very important, is the temperature coefficient of power and voltage. How will the power change if I increase or I decrease the temperature? And also you can study the thermal stability. Because this is very important for us. It doesn't make sense to make a cell and you find that the power, the temperature coefficient of power is higher than that of silicon. It doesn't make any sense. Because silicon, as I'll show you the numbers here, for silicon it's about 0.4% per degree C. So these temperature coefficient of power should be low. Okay. Another parameter that we can measure is also how the conversion efficiency changes with the photon wavelength. And we measure what we call the external quantum efficiency. Ideally, the external quantum efficiency should be just a rectangle, because once your wavelength is below this threshold, the response should be 100%. Okay. It means if the quantum efficiency is 100%. So each photon will give you electrons. So the quantum efficiency, what you call the quantum efficiency is 1 or 100%. But this is in the ideal situation. Okay? But in reality, you have some losses. As I told you, you see, these are red photons that are absorbed at the back surface, near the back contact. The blue photons here are absorbed near the front contact. So if there is a reduction in the signal or in the quantum efficiency, that means that you have problem either in the front contact here, or you have a problem at the back contact, or if you have a reduction here also in the above, that means you have some problems within the axial layer. So you have to figure out what's happening there. So the quantum efficiency is very important parameter to measure for solar cells, because it gives you somehow what is happening at different parts of your solar cell. Just informs you what is happening. These are some measurements that we made for amorphous silicon, for perovskite, for silicon in red. Okay, as you can see here for silicon, because the threshold for silicon is is around 1,100 nanometers. For perovskite here, the threshold is about 800 nanometers, and for amorphous silicon, that amorphous silicon has a band gap of 1.7, so the threshold is a bit low. Okay, so I'm just going to show you the standard silicon solar cell. As you can see, it resembles the theoretical solar cell I showed you in the beginning. So it is made of what? Of a P-type here absorber. It's a silicon wafer. It is just textured here just to enhance what we call light trapping within the semiconductor. Because if there are photons that are not absorbed, they cannot escape. They'll be reflected by these asperities inside the semiconductor. So this is a way to enhance what we call light trapping. But anyway, it's a P-type, textured. The surface here is doped N+, the back surface is doped P+, and you have here an anti-reflect coating, okay, just to reduce the reflection, and then you have your contacts. So this is the standard silicon solar cells that you can find in the market. You can see here these contacts, these fingers. These are called current collectors, and you have the back contact also, which occupies all the whole surface. But this is a monocrystalline solar cell, and this is a polycrystalline, and you can see in the polycrystalline you see a lot of crystals. And for this cell, I mean the open circuit voltage is around 0.6 volt. Okay, the efficiency maximum is 22%. And the thickness, the cell thickness, you see it's about 150 to 200 micron. And I told you that the absorption depth for silicon is what? Is 100 microns. So you see the thickness is higher, and the area of the cell is about 15.6 by 10, 15.6. You have also surface texturing, etc. Okay? So this is called aluminum back surface heat, because this P+ layer here is created because the back contact here is made by aluminum, but when you heat up the aluminum here, it will diffuse into the semiconductor, into the silicon, and give you a P+ layer, because aluminum will dope. It is a group 3 element, like boron. So it will dope it. This is phosphorus here, and this is aluminum. Now, what is the problem with this is you have a lot of defects at the surfaces here and here. So we have to, the next generation technologies of silicon, they will try to passivate the surfaces using a lot of, I'm not going to explain it, but you can see the techniques here, the top con that Professor Wahidi talked about, the PERC technique. Okay, you see here you have what we call a capping, a silicon nitride passivating layer, okay? And then you have localized contacts here. Why do we use localized contacts? So that the area is not too big, so that means you wouldn't have a lot of defects. So you see you passivate here the back contact, and you passivate also the front contact in order to reduce recombination, or surface-induced recombination. So this is the pair, the same thing for the pair. So you passivate, okay, and you make some local contacts here. This is easily done with a laser scribing. So you just deposit here an insulator and they scribe these with the laser, and then you put the aluminum and you fire everything. So the aluminum will diffuse and will create the P+ zones here. So as you can see, all this part here is passivated. So it will not contribute to the recombination. If you have a recombination, probably it will happen just in this area. So this is the PERC, the PERC, etc. And the top cone also, you mentioned the top cone, the back contact technology, the heterojunction. You see the heterojunction, just you take the silicon wafer, okay, and you sandwich it between two layers of amorphous silicon. So these are the passivation layers. You put amorphous silicon here, very tiny layer, so that electrons, they can cross these layers but just by Canada effect. Even if it's resistive, since it's very thin, they can cross. And then you make your heterojunction here between the P+ amorphous silicon and the N-type here silicon. But you see, it's the same structure. You have an absorber, N+, P+. It's the basic structure they showed you in the beginning. The same thing for the front contacts. These contacts are just managed at the back, okay, of the cell. No contacts are made at the front, so that you reduce the shading effects due to the current collectors. Okay, so I'm going to go to record efficiencies now in solar cells. Last year, Longi has reached 27.3% efficiency in silicon. And you see that for silicon, the maximum thermodynamic efficiency is 30. So we are 2 points from the maximum. So yeah, that's why all the innovations, are still just done in the what we call the passivation and of the solar cell. Okay. And just in April, I just checked their news. In April, they enhanced this to 27.1%. They gained about 0.5%. Now, just have to give me 10 more minutes. Huh? Okay. I need 10 more minutes. I don't know if I consumed all my time because it's half an hour. Oh, really? Okay. Okay. So now, let me just go back to perovskites rapidly, because all what I wanted to tell you about perovskite I already said, because I just talked in general. What I said is also valid for perovskites. Okay. Perovskites are a type of material that have a formula ABX3, where A is usually an organic or an inorganic cation, methylammonium or formamidinium or cerium or rubidium, and B is usually lead cation, it's a metallic cation, lead or tin, and X is a halide, okay? And if A is an organic, those are called inorganic, hybrid perovskites, okay? With hybrids, you have organic and inorganic. And you also have chalcogenide perovskites, where A is barium and B is zirconium and titanium and so on. So why perovskites are so interesting? Because usually they are direct band gap, so they have very high absorption coefficient, as I showed in that graph. Okay, the band gap is tunable. You can tune it, change it, just acting on the materials, on the elements, and they also have very long diffusion length. So, the thickness that they need is not that high. Okay, and also they have very high charge carrier lifetime and high dielectric constant. Low excitant Biden energy, exactly like silicon. It's about 10 to 15 millicron volt. And the diffusion rate, they can exceed 5 microns. And they also easily produced by just solution processing. Okay. So the global perovskite market is a market that is very in constant increase, and it increases on the average at a rate of, or it is projected in fact, to increase at a rate of 6.3% between 2023 and 2031. Okay, so there are a lot of market drivers for this perovskite material market, like electric vehicles, and so on. Okay, so these are also some graphs from the market. As you can see, that the perovskite technology will start to be marketed, let's say, at the end of 27, because there are already some modules that are made, but they are not yet commercialized. Okay, but it is expected that the market share of perovskite in the global PV market will increase. Okay. So the solar cells, they have the same architecture as I showed again. So you have your absorber sandwiched between two layers and the contact. The only difference, sometimes you make also a mesoporous heterojunction where you deposit the absorber on mesoporous contacts so that you increase the surface area, the contact surface area. But sometimes this is also a problem. Okay. Yeah, so these are some cells that we made at the lab, okay, and we reached in the lab 20.3%, but we used this inverted thing, just the comparison between silicon solar cells and the perovskite solar cell. You see the perovskite has a high open circuit voltage than the silicon solar cell, but the current density is lower anyway. So if you want voltage, use that. Perovskites, they can be prepared by a lot of techniques, including solution processing, physical vapor deposition, large slot day coating, and so on. Okay, so I'm not going to talk about this. The latest efficiency in perovskite source is 26.7. You can see it's very close to the silicon, which is 27.3 now. So it's very competitive with silicon. The only problem is with perovskite, you can check this graph. It's updated every month. I think you'll find that the new recall efficiency for silicon Donji's recall efficiency here. The only challenge is the problem with perovskite is the stability. The stability and also the upscaling. You have to upscale the process. The stability is a very issue because you have environmental degradation. It's also unstable when you heat it up or you expose it to UV. You have a lot of ion migration and so on. The problem is lead also is very problematic. Okay, so people now are trying to substitute lead with other materials and so on. Scalability also is a problem. Spin coating is not, you cannot industrialize it, so you have to do either just printing or slot die coating, but you have to eliminate the solvent and so on. So there are lots of other problems that needs to be solved, and the golden triangle for solar cell, the cost, the efficiency, and also the lifetime. You see that silicon and perovskites, they have almost the same efficiency. The cost of perovskite is probably lower than silicon, but the problem is the lifetime. So it is some cells with 10,000 hours of lifetime have been already produced, but this should be still pushed further, because for silicon you get a warranty for 25 years, at least. 25 years, that means your efficiency will decrease by 20%. Okay.
Your lifetime is finishing?
Finishing, yeah. Okay, anyway, it's okay. But they said the essentials, so what they said about the stability, and it's also valid for perovskites, okay? I didn't, maybe if you allow me one last slide to show you the next, because this is the stability, and then, the latest breakthrough here for tandem solar cells, it's just in April again, they reached 34.85. But this is for tandem. That means it's for two-cell configuration. We have a perovskite cell on the top and the silicon cell in the bottom. Okay? So they reached now 34.85 efficiency again. Okay. So maybe you'll find this in the table, in the NREL table for this month, this breakthrough. Okay, thank you very much.
Thank you, Abdel. So, if you have any questions, okay, start.
Thank you, Professor Ashkadar. I have one question. For panel made with perovskite, are they now commercialized or not?
Not yet. There are some companies that they are advertising these the tandem ones, but they are not yet in the market. They said we've made this and that, but they are not yet in the market.
This is the tandem.
Yeah.
But for only perovskite.
Not only perovskite, not yet, because there are some issues because with the stability.
The technology readiness level. What level?
Let's say the problem is not the technology readiness level, because Oxford has been making modules, but the problem is the stability issue. They only make panels, they probably last, and there is not a return on experience yet. No, they already did lab to fab or whatever they call it.
Lab to fab.
They're at that stage, but the problem is the stability. The stability is still an issue.
Thank you.
And the stability is linked to all what they said about the defects, about how to passivate, how to. Okay.
To finish. Great presentation. My question is very short. For all the cell efficiencies you mentioned, Ganja and the perovskite cell which you mentioned, what's the cell area? Because most of the time I see people would mention for the contact, but that's not true efficiency of the cell. So I just wanted to see what's the area.
All the efficiencies that are reported in the NREL table, they're for 1 square centimeter. Evidently, if you go to large areas, you get lower efficiencies because a lot of other defects that you have to. And if you go to panels, you have a lower efficiency in fact. But it's 1 square centimeter. For us, it's even less than that. In our lab, we don't make 1 square centimeter, but we make let's say 1 point something. I don't remember.
So in mid-1985, I worked for a company called Spark Corporation. They are one of the largest producers of solar cell, or at least at that point. We had mentioned in NREL that whenever people mention efficiency, they must mention the cell area.
You're absolutely right. Luckily, I was based on the NREL table, and that it's standard. It's 1 square centimeter.
Thank you.
Thank you.
Maybe the cells I cheated when I mentioned that myself because the area is lower than that. Yes. No. Yes.
Right.
Yeah. You're absolutely right. Yes.
Always in the STC condition.
Yeah. 1,000. Yeah. Not STC. Just the irradiance should be 1,000. The spectrum should be 1.5. If you STC, you have to cool the cell to 25 degrees. Yes.
Okay.
But
let's think again.
Thank you.